Okay, so in this video, I'm going to attempt to do my best to explain the idea of a sampling distribution. Now, the idea and the concepts of a sampling distribution tend to be some of the most abstract and difficult for students to grasp. And so I'm going to apologize in advance if I can't clear it up for you, but I'm gonna try my best. So let's start off by first just going over the formal definition of a sampling distribution, which you may read in like your textbook. This is the one that I have in my textbook that I use, which says that the sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. Okay, so let's start off by you know going through like a hypothetical study, like we're trying to answer some question. So let's say we want to figure out what the true proportion of high school students that smoke weed is. So we want to find, let's say, the true value of population parameter P, which is the true proportion of high school students that smoke weed. Now, like, how would you go about answering this? We obviously can't go and ask every student in the US and gather data, because that would take forever. It'd be impractical, impossible. It wouldn't be worth it to go through. There's millions of high school students. So what we would do is take samples. We would take samples and ask students and in those samples if they smoke weed or not. And then from there we would gather sample statistics. So let's say you gather you take a survey from 100 students and ask if they smoke weed at your school, and you get a sample proportion of 0.17. So 17 of the 100 students say they smoke weed. So your sample statistic is 0.17. Now let's say your friend, another high school, takes also a sample of size 100 at their school, and they instead get 0.16. Similar but different. And then let's say your other friend who goes to a different high school takes a third sample and gets sample proportion of 0.20, and so forth. Let's say you manage to get 50 samples. 50 samples where each sample, let's say the 50 sample, let's just say it's 0.19. Now, each sample has to have the same number of students for it to fit a specific sampling distribution. So each sample has to have a size of 100. Now, the sampling distribution of this would be essentially a picture of a graph. So what we could do is make a dot plot. Make a dot plot. Say it's let's say this is 0.19. This is 0.18, 0.17, 16, and so forth. 0.20, 0.21. And then you would plot, plot all your data as a dot plot, and maybe it's looking something like this. Again, this is just a hypothetical example. You're gonna see some pattern emerge. Now, of course, you're gonna have outliers and maybe some skewness or something, but you're gonna get some pattern. You're gonna get some shape, and this graph, this pattern, this distribution is what we call the sampling distribution of the sample statistic p hat for the specific size of 100. That's why we say same size. This will have to all come from samples of size 100. Because again, if we wanted to have another sampling distribution, let's say if we want to have if we were to take samples of let's say 50, it would be a different distribution. We couldn't mix the samples of size 50 with the samples of size 100. So this is a sampling distribution of p hat where n is 100. Now, more specifically, this is just an approximate sampling distribution. an approximate sampling distribution because the true sampling distribution has to include all of the possible combinations of 100 students in a population. The true sampling distribution would have like millions and millions and millions of values because there's so many different combinations of size 100 that you can get from the population that we couldn't do this in real life either. But what we can do is we use simulations. We like to use computers to run this, and that will give us an idea of what it would look like. And what we're going to learn about sample proportions is that this is an unbiased estimator. We're going to talk more about that and later on, but it's an unbiased estimator, which means that the approximate sampling distributions will be centered at the true population proportion. So if it was to look something like this, we could then say the true population proportion is about 0.2. That's what's so great about it. That's the genius, and that's the greatness behind sampling distribution, because this is how we can actually figure out what the true proportions are, the true population parameters are. In this case, the population proportion. So let's look at it. Let me use another example. Like I'm gonna have this poker chip bag here, and I'm gonna try to figure out this poker chip bag. I want to figure out what's the true proportion of red chips. True P of red chips. So in this population, the population has, I have 200 chips in here, 200 colored chips. And I'm going to take samples of size 20. So let me just do one example, just so we can take 20 chips. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 chips. Out of those 20 chips, I have 1, 2, 3, 4, 5, 6, 7, 8. So in my first sample, I get that 0.4 of them are red chips. Now let's say I take another sample. Like it's possible I can get 0.4 of them to be red chips. Now also know that I'm selecting samples at random, which means it's possible that I can select the same chips or some of the same chips again, and that's okay, because again we want to have all possible combinations of size 20. So let's say in this one I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. And my second sample of 20 chips, I have 3, 4, 5, 6, 7, 8. I have 8 again, coincidentally. So my second sample, I have 20. Oh, I have 8 chips of 0.4 of them are red chips. And again, I can keep on doing this. I usually will do this as an activity for my students so they can really get the idea of a sampling distribution, because again, you really want to do hypothetical examples when you're learning about sampling distributions, because it is an abstract concept. Now again, this is going to make us, this is a specific sampling distribution for samples of size 20. Now again, why do we use simulation? And when I was saying like, oh, there's so many possible combinations, if you have any, if you've already learned combinatorics, well, let me look at I've actually calculated this and created a distribution. And in this dot plot, I graphed 35 samples of size 20. And here I have the proportion of red chips in each sample. I got anywhere from 0.2 to 0.7. And I actually calculated the mean to be right about 0.5, right about 0.499. Even the standard deviation I calculated. Now, again, why we can only get approximate sampling distributions and why we need to use computer simulations is because there are actually 1.6 times 10 to the 27 possible combinations of samples of size 20 just from 200 chips. This is I don't even know how, I can't even fathom how big that number is. It's a 10 or 27 zeros. Just from 200 chips. Imagine if there are 1,000 chips. And that's just gonna be something we're gonna need to use. And the good thing again is that it doesn't actually matter. From these 35 samples, I actually got right on the true proportion. The true proportion given away here is actually 0.5. Is 0.5 is the true proportion of red chips. And from those 35 random samples that I took, I basically, created a distribution that was centered right at 0.5 just from 35 samples. So again, that's the beauty of sampling distributions, and that's why we want to use them and become, very good at understanding them and applying them. So I hope that helps.